All right, time to get all trippy. We're going to talk about higher dimensions and dimensionality reduction. Sounds scary. There is some fancy math involved, but conceptually it's not as hard to grasp as you might think. So let's talk about dimensionality reduction and principal component analysis next. Let's talk about the curse of dimensionality. Very dramatic sounding. Usually when people talk about this, they're talking about a technique called principal component analysis and a specific technique called singular value decomposition, or SVD. So PCA and SVD are the topics of this lecture. Let's dive into it. So what is the curse of dimensionality? Well, a lot of problems can be thought of having many different dimensions. So for example, when we were doing movie recommendations, we had attributes of various movies, and every individual movie could be thought of its own dimension in that data space. So if you have a lot of movies, that's a lot of dimensions, and you can't really wrap your head around more than three, right? Because that's what we grew up to evolve within. Or you might have some sort of data that has many different features that you care about. In a moment we'll look at an example of flowers that we want to classify, and that classification is based on 4 different measurements of the flowers. And those 4 different features, those 4 different measurements can represent 4 dimensions, which again is very hard to visualize. So dimensionality reduction techniques exist to find a way to reduce higher dimensional information into lower dimensional information. And not only can that make it easier to look at and classify things, but it can also be useful for things like compressing data. So by preserving the maximum amount of variance while we reduce the number of dimensions, we're more compactly representing a data set while still trying to preserve the variance in that data set. So very common application of dimensionality reduction is not just for visualization, but also for compression and for feature extraction. And we'll talk about that a little bit more in a moment. A very simple example of dimensionality reduction can be thought of as k-means clustering. So, for example, we might start off with many points that represent many different dimensions in a data set, but ultimately we can boil that down to k different centroids and your distance to those centroids. So that's one way of kind of boiling data down to a lower dimensional representation. But usually when people talk about dimensionality reduction, they're talking about a technique called principal component analysis. And this is a much more fancy technique. It gets into some pretty involved mathematics, but at a high level, all you need to know is that it takes a higher dimensional data space and it finds planes within that data space in higher dimensions. And these higher dimensional planes are called hyperplanes. And they are defined by things called eigenvectors. And you take as many planes as you want dimensions in the end, project that data onto those hyperplanes, and those become the new axes in your lower dimensional data space. Unless you're familiar with higher dimensional math and you've thought about it before, that's going to be hard to wrap your head around, but at the end of the day, it means that we're choosing planes in a higher dimensional space that still preserve the most variance in our data and project the data onto those higher dimensional planes that we then bring into a lower dimensional space. Okay? You don't really have to understand all of the math to use it. The important point is that it's a very principled way of reducing a data set down to a lower dimensional space while still preserving the variance within it. We talked about image compression as one application of this. So, if I wanted to reduce the dimensionality in an image, I could use PCA to boil it down to its essence. Facial recognition is another example. So if I have a data set of faces, maybe each face represents a third dimension of 2D images, and I want to boil that down, SVD and principal component analysis can be a way to identify the features that really count in a face. So it might end up focusing more on the eyes and the mouth, for example, as important features that are necessary for preserving the variance within that data set. So it can produce some very interesting and very useful results that just emerge naturally out of the data, which is kind of cool. To make it real, we're going to use a more simple example using what's called the iris data set. And this is a data set that's included with scikit-learn. It's used pretty commonly in examples. And here's the idea behind it. So an iris actually has 2 different kinds of petals on its flower. One's called a petal, which is, the flower petals you're familiar with. And it also has something called a sepal, which is kind of this supportive lower set of petals on the flower. And we can take a bunch of irises in different species of iris and measure the petal length and width and the sepal length and width. So together, the length and width of the petal and the length and width of the sepal are 4 different measurements that correspond to 4 different dimensions in our data set. and I want to use that to classify what species an iris might belong to. Now, PCA will let us visualize this in 2 dimensions instead of 4, while still preserving the variance in that data set. So let's see how well that works and actually write some Python code to make PCA happen on the iris data set. So that's the concepts of dimensionality reduction, principal component analysis, and singular value decomposition. All big fancy words, and yeah, it is kind of a fancy thing. You know, we're dealing with reducing higher dimensional spaces down to smaller dimensional spaces in a way that preserves their variance. Fortunately, scikit-learn makes this extremely easy to do. Like 3 lines of code is all you need to actually apply PCA. So let's make that happen.